Here in chapter 11, we're going to shift gears and we're going to start talking about sequences and series. So sequences will be essentially a type of function where each term of a series corresponds to a particular value of that function. And what a series is it looks at adding up infinitely many terms of a sequence. So in the first section here, we're going to just focus on what a sequence is. One way to think of a sequence is as an infinite list of numbers, A1, A2, A3, A4, and so on. And notice that the way that we're denoting each term of the sequence is with a subscript that tells us in which place that particular term occurs. So for instance, A1, we would call that the first term. A2, we would call that the second term. And so on. A3 would be the third term. Of course, AN would be the nth term. So this will be a standard way to denote the terms of a sequence. And like I was saying earlier, we can think of a sequence as a function. In this case, it's not a continuous function that can take on any value of x and spit out a number. Instead, it only takes input values that are natural numbers, right? So for instance, the function at 1 is a1, the first term. The function at 2 is a2, the second term, and so on. So we can think of here our nth term an is really some function of n, where n is a natural number. More generally, n could potentially be an integer that also takes on negative values, but here we're mostly focused on these cases where n is a positive integer. So notation will vary. For instance, we could have notation where we list out the terms of the sequence in curly braces, which the curly braces is really just denoting the sequence. Oftentimes you'll see curly braces used to denote a set, but it's important to distinguish that a sequence is not really a set. A set is just a collection of objects, but a sequence is really an ordered list. And so the order that we're listing these values in is actually important. Okay. When I put curly braces around some expression involving n, we assume that that expression tells us the nth term of our sequence. So we'll also see this notation, curly braces around an. And then sometimes we might need to indicate where the sequence begins and where the sequence ends. So for instance, if I say an with n equals 1 infinity, that means it starts with n equal to 1 and goes forever. So you may need to define it differently depending on how you're defining your sequence. You may indicate that it starts with some other index other than n. So let's just look at a couple of simple examples. And here we're looking at it in a couple of different notations. Notice in this first notation here, for the first one, we've got the nth term formula n over n plus 1, ranging from n equals 1 to infinity. And here's that nth term formula, an equals n over n plus 1. So this is just the formula that generates each term of the sequence. And so by substituting in values for n, we can get specific terms of the sequence. For instance, at n equals 1, we get 1 over 2. At n equals 2, we get 2 over 3. At n equals 3, we get 3 over 4, and so on. So these are just really a list of all those terms. So a1, a2, a3, and so on. Okay, so in the next one, we have -1 to the n plus 1 over 3 to the n. So again here, putting it in curly braces means we're describing the nth term formula in the curly braces, or I can just simply write an equals that formula, and here we see the terms listed out. So again, notice that here they don't indicate where it starts and where it ends. So by default, we suppose that the sequence starts at n equals 1 and goes forever. And so we can see here, yeah, when n equals 1, we'll have -1 to the 1. 1 plus 1 is 2, so we have -2 over 3. And then when n equals 2, we get -1 squared is +1. 2 plus 1 is 3. Over 3 squared is 9. So we get 3 over 9. And so on. You can continue putting in different values for n, and that will generate more and more terms of the sequence. One thing you might want to notice here is that this factor -1 to the n will switch between positive and negative every other term. So for instance, when n is odd, it's going to be a negative value. So like when n equals 1 or when n equals 3, we get negative values. And when n is an even value, then -1 with an even power will be positive. So we see all the even index terms like a2 and a4 all have positive values. So we'll see that in the future that this -1 to the n factor will create what we're calling an alternating sequence, where the terms alternate between positive and negative. In the next example, we see the square root of n minus 3. Notice here that we have to indicate that the sequence really starts with n equals 3. Right? Because if I started with n equals 1, you would have something undefined, or actually not a real number for n equals 1. Because then I would have a negative number under the square root. So in order to get this to be a sequence of real numbers, we need n equals 3 to be the first value. Okay, and so we've indicated sort of the alternate way to notate that here. An is the square root of n minus 3, with n greater than or equal to 3. And of course, listing out the terms, we see that when n is 0, 3 minus 3 is 0, so we get the first term is 0. So notice here the first term is really a3. And then the next term would be a4. And the next term would be a5, and so on. So here, because it doesn't start with n equals 1, our first term is not a1. Our first term is really a3. Something similar here in the next example. Notice we're not starting with n equals 1, but now we're starting with n equals 0. So here the sequence is generated by cosine of n pi over 6. So when n equals 0, we'll start with cosine of 0 for the first term. So a0 here would be 1. When n equals 1, that would give us the next term of the sequence. So cosine of pi over 6, right, would give us our next term. And then a2 would be the next term. So cosine of 2 pi over 6, or cosine of pi over 3, is 1/2. And so on. So you can continue putting in different values for n, and those would generate each subsequent term of the sequence. So what's nice about having an nth term formula is now I have an explicit formula that gives me every term of the sequence. So for instance, now if I want to go out to a specific term of the sequence, say a20, then I would just need to plug n equals 20 into the formula. And also, this is more of a more familiar way to think of it, because it's really defining it as a function, right? Here, in each case here, an is defined as a function of the variable n, where n here, again, is some integer value. Some of them start at different values, but by default, we assume n starts with n equals 1, and then continues up from there, n equals 2, and so on. Okay, so this is a very common way that we'll look at a sequence. We'll see that there are actually other ways to define a sequence, but this will be the most useful and the most common way of doing it. Suppose now I want to find a formula for the nth term of the sequence given in the list here. We've got 3 over 5, negative 4 over 25, 5 over 125, negative 6 over 625, and 7 over 3,125. Now, one way to look at this is to see if you can figure out a pattern going from one term to the next. And in the numerator, there's a pretty easy pattern to notice, that it's going up by 1 from one term to the next. The pattern in the denominator might be a little bit trickier to see, but just actually looking from the first term to the second term, we notice that it's being multiplied by 5, so it's starting with 5, and then the next term would be 5 squared, and then the next term after that would have 5 cubed in the denominator, and then the next term after that would have 5 to the power of 4 in the denominator, and then 3,125, that's the same as 5 to the power of 5. So the pattern here is that we're looking at powers of 5. Where here this is 5 to the 1, 5 to the 2, 5 to the 3, and so on. And one other thing we want to notice is the alternating sign. It starts with a positive value on the first term, a negative value on the second term, positive value on the third term, negative value on the fourth term, and so on. So the sign is alternating positive, negative, positive, negative. So that's another thing that we have to indicate in our nth term formula. Okay, so now that we've kind of described the pattern here, let's try and write that symbolically. So with the first one, that's well, we can think of that as 3 over 5 to the power of 1. The next term would be negative 4 over 5 to the power of 2. The next term would be 5 over 5 to the power of 3. The next term would be negative 6 over 5 to the power of 4. And this would be 7 over 5 to the power of 5. So it's kind of easy to see that the denominator for the nth term formula here would most likely have something of the form 5 to the power of n. Right? Because we see there that when n is 1, we get 5 to the 1. When n is 2, we get 5 to the 2. When n is 3, we get 5 to the 3, and so on. Now, how do we get the numerator? Well, one thing to notice is that if I'm starting with n equals 1, the first numerator would be 1 plus 2. And then the second numerator would be 2 plus 2. The third numerator would be 3 plus 2. And this numerator would be 4 plus 2. 5 plus 2, so on. So you notice that here in the numerator, it's going to be, as n goes up, we're adding 2 to n. So it'll be something of the form n plus 2 in the numerator. And then we also need to indicate the alternating sign. And remember, we had a nice way of doing that with negative 1 to the n. But in this case, we want the first term to be positive. So I'm going to put n plus 1. So that when n equals 1, we get negative 1 squared, starts with a positive value. Then when n equals 2, you get negative 1 cubed, which is now a negative value. So this is going to make it start with a positive value for n equals 1. And then it'll alternate between positive and negative for the terms after that. So here's one way to write it.